Okay, welcome to lecture 17 and 18. So previously, we have studied work. So work done depends on the force applied and the distance moved by the force in the direction of the force. So that's where the angle theta comes in. Angle theta is the angle between the force and the delta x. And work done creates change in energy. So delta U is change in energy that's brought about by doing work. This work can be positive or negative or zero, so that would change the energy positively, negatively, or won't create any change. Then we looked at types of energy. So we have two types of energies principally. We have kinetic and potential. Okay, so kinetic energy has to do with motion. Any moving object has kinetic energy. And then potential energy is stored energy. It can be stored in different forms, such as gravitational potential energy, spring potential energy, chemical potential energy, electrical potential energy, and so on. So in this class, we'll be studying gravitational and spring potential energy. Okay? The equation for kinetic energy is this. K, kinetic energy equals half times mass times speed square. And the equation for gravitational potential energy is Ug equals mgy. Okay, and where y is the height measured from some reference point, which we call y equals 0. Okay, now we know that when we do work on a system, the energy of the system changes, which also means if we have an isolated system, and the word isolated means then it's not interacting with anything outside the system. Okay, so think of objects like in a box, for example. The objects are acting only with themselves, nothing not with anything outside the box. That would count as an isolated system. So if you have an isolated system and there are no external forces or torques acting on it, so there is no external work done on the objects in the system, then we say the total energy of the system is conserved. Okay, and you write it like this, that you can factor in the change in all types of energies: kinetic, gravitational potential, spring energy, thermal and chemical, and all the other ones that you know of. The changes in all these energies added together must be equal to 0. Okay, so that's basically saying the energy in the system should not be changing. It can change from one form to a different form. For example, some kinetic energy can become gravitational potential energy, or some gravitational potential energy can become spring energy, or any of the combinations here. But when you add up all the energy of every type, you will see that they add up to the same constant value. They are not changing. So this is also known as the equation down here, that the energy of the system at some initial point equals the energy of the system at a different point, different time. So initial energy equals final energy. That's what conservation of energy says. And this applies when there is no external work done on the system. So that means there is no external forces or torques. So there is no external agent that applies a force or torque on the system and does work on it. Okay, so you can look at this simulation that describes conservation of energy. So in this diagram, you can see that we have water. So we have water particles that are traveling and they're carrying energy. They're carrying kinetic energy. So as the water hits this wheel here, the wheel turns. So effectively, the water is transferring kinetic energy from itself to the wheel. Okay, so that's what makes the wheel rotate. Okay, but remember that any sort of motion has kinetic energy involved. So energy from the moving water is transferred to the energy of the wheel, makes it move. Okay, and the wheel is connected to a generator. So the generator converts the rotational motion of the wheel to electrical energy. So you can see this little tiny boxes of energy marked with E. They're traveling through the wire as the electric energy. And then the electric energy heats up this water heater. Okay, so as the water is heated, the electric energy is converted to thermal energy. So this thermal energy heats up the water. So thermal energy from the heater is transferred to the water particles in the container. Okay, and these water particles get heated up, and if they boil, so some of them will travel up, carry some of the energy with them as steam. Okay, so in this process, you can see energy is being converted. So energy is converted from kinetic to electrical, then heat, and then to other forms. So energy conversion happens all the time. depends on the system you're looking at. It can go from kinetic to potential, or potential to kinetic, or in a number of different ways. However, if you can count the total number of energy boxes here, the little tiny boxes, you will see that the total energy is the same all throughout. Okay, so the number of energy blocks that are coming off the tap, and if you count the energy in the rest of the system, you'll see it's the same number of energy boxes. Okay, so this gives us what we studied in the previous slide, principle of conservation of energy. That means energy is transferred from one form to another, but the total amount of energy is constant in a closed system. Okay. Okay, so here let's look at a specific example, energy conversion from kinetic to gravitational potential. Okay, so you can launch this simulation. So we have this track, and this track is frictionless, let's assume, and we have a skater who starts from up here. Okay, so that's his initial position. Okay, and once you release the skater, he's traveling down. Okay, and as he's traveling down, he's gaining speed. Okay, so he's gaining speed as he goes downwards, and at the same time he's losing height. Okay, so his height is dropping. So in terms of energy, what we see is shown by this bar chart here, that close to the top of the track, the potential energy of the skater is maximum, well, close to the maximum, and then as it travels downwards, the potential energy decreases because his height is decreasing, but at the same time the kinetic energy increases. So you will see that the green bar for kinetic energy goes up as the skater goes downwards. Okay, so this is an example of energy conversion. And the last bar here in the chart, the total energy, you will see that the total energy remains constant all throughout. Okay, so sure, that part of the energy can be kinetic, part can be potential, and it changes as the skater travels along the ramp, but the total amount of energy doesn't change because the skater is losing potential energy and is gaining kinetic energy. So the energy changes happen within the skater. There is no contact with the external world. Okay, so that's why there is no external work done on the skater, and the energy of the skater is conserved as long as it travels on the ramp. Okay. Okay, so let's look at two snapshots here. So on the left, we have the skater at the very top of the ramp, just when he's starting. Then at a different time, we have the skater at a different point, about 2 meters above the bottom. Okay, so we'll call this the initial state on the left, and on the right, we'll call that the final state. So let's find the initial energy of the skater when he's up here at 6 meters. Okay, so when he's at the initial position, he's not moving. Okay, so he only has gravitational potential energy. Okay, so the skater is at zero velocity. So if the speed is 0, that means the kinetic energy is 0, and the skater only has gravitational potential energy. All right, and let's assume that gravitational potential energy has a 0 reference at the bottom at y equals 0. So this initial height is going to be 6 meters. So his initial energy is the initial gravitational energy is mg times y. Okay, so we don't know the mass of the skater. We don't, and g is 9.8. But let's just put them in symbols for now. We'll solve later. Then let's look at the second snapshot. That's the final state. And here, the skater is moving. He has some velocity going roughly downwards. Okay. So now the skater has kinetic energy, and the skater still has some gravitational potential energy because he hasn't reached the bottom yet. So his final energy is part gravitational, part kinetic. You write it like this, Ug plus K. So we can find what the gravitational potential energy is. So we can use mg times y, just that this y should be 2 meters this time because we're looking at the height at this location. So his final energy is going to be Ug final plus kinetic final. And then you plug in the equations for Ug final and kinetic final. Okay, so that's Ug final is mg y final, kinetic is half times m times v final square. Okay, so we don't know what v final is, but we can find it using the energy conservation principle. So we have an expression for the initial energy in terms of y initial, and we have an expression for the final energy in terms of y final and v final. Okay, and from the conservation of energy, we know that the total energy of the skater must be the same, which means the energy at the initial and the energy at the final states must be the same. So let's set the energies equal to each other. Set initial equals final energy. Okay, so ui equals uf, and then plug in the expressions. So ui is the expression on the left, uf is the expression on the right. Okay. Then we can rearrange the equation. We are trying to solve for v final. So rearrange the equation, try to isolate v final, and you can see in the process the mass cancels out. Okay. So we were not given the mass of the skater, but it turns out that we don't need the mass of the skater. It cancels out. So we can solve this problem without knowing the mass of the skater. Or in other words, it doesn't matter what the mass of the skater is, you'll end up with the same speed. Okay. So going back to the problem, you cancel out the mass, then you solve for v final, so take the square root. Okay, and then plug in the numbers for y final and y initial. Okay. And also plug in the value of g, and the calculation will give you 8.85 meters per second. Okay, so that's the speed of the skater when he's 2 meters above the ground. Okay, so he started with 0 speed, and then as it goes downwards, his speed increases. Okay, all right. So this is an example where you can find the speed using conservation of energy. So notice that we don't know what the shape of the track is. Okay, it can be a parabola, it can be some other shape, but it doesn't matter. All we need to know is the initial state and the final state. Okay, so it doesn't matter how he got there as long as there is an external work done. If we know the initial state, if we know the final state, and it doesn't matter what the track looks like or how we got from initial to final, we can use conservation of energy and set the initial equals final energy. So that gives us an equation that relates the types of energies and the different quantities that depend on. So that relates the speed and the height and so on. And that gives us a useful tool for finding the speed, for example. Okay. Then here, continuing from the previous slide, we look at 2 other snapshots. On the left, we have the same snapshot from the previous slide. And then on the right, we have a new snapshot where the skater is at the very bottom of the track. Okay, so we're going to find the speed of the skater at the very bottom. So we'll take these 2 snapshots here, call this the initial on the left and final on the right. And like before, we calculate the initial energy. So we have done this already in the previous slide. At this state, the skater has some height above the ground, above the reference, and he also has some speed. So the skater has part gravitational, part kinetic energy. Okay, so we already know what the speed of the skater is as well at this point. So the speed is 8.85 meters per second. We'll call it v initial, and the height we'll call y initial. Okay, it's 2 meters. So we can write down the equation for initial energy. We get mg y initial plus half times m times v initial square. Then for the final energy at the very bottom, the skater only has kinetic energy. And that's because the skater is at the ground level at a height of 0. So if he's at the height of 0, that means he doesn't have any gravitational energy. He only has kinetic energy. So the final energy is only kinetic. So U final is half times m times V final square. So again, we have 2 expressions, one for the initial energy, one for the final energy. So now we set them equal to each other. So set U initial equals U final. All right, so like before, we can see that the m cancels out on both sides of the equation, okay, because you can divide by m and it will cancel out. Then you're solving for v final. So rearrange the equation, solve for v final, take the square root, plug in the values, and you get 10.84 meters per second. Okay, so that's the speed of the skater at the very bottom of the ramp. Okay. And as expected, this speed at the bottom is bigger than the speed at the 2 meters height. Okay. So again, it's the same benefit of using the conservation of energy, that you don't have to know what the shape of the track is. All you need to know is the initial position of the skater and the final position, and then you can calculate the initial energy and the final energy, set them equal to each other. So very useful tool. And the other important thing about this is that there is no time involved anywhere. So this question and this method only gives you the speed. Okay, So if you are trying to find the time it takes for the skater to go from top to bottom, then this method won't give you the answer. So conservation of energy won't give you the time. It can be used to find the speed or the height. Okay, so not time, because the energies don't depend on time. And if you do want to find the time, then you have to resort to the equations of motion. Okay, ones with the acceleration and so on. So let's look at this example of the energy conservation of car traveling downwards. So here the car is sitting at rest at the top of a hill, and then it's pushed, so it's not running its engine, it's traveling on its own. So the car rolls down the hill by 5 meters, okay, and it's moving at some speed when it travels downwards. Okay, so like in this animation here. So we are trying to figure out the equation of conservation of energy, and then also note down the choice of system and the initial final states and what energy transformation takes place. Okay. All right, so we can see that there's a change in height, so it makes sense to define a y-axis showing you the change in height. Okay, so let's say the final state is y equals 0. That's where the car is at the end, and the initial state, let's call it y equals 5 meters. So that's where the car started off. Okay, so we can calculate the initial energy, which is just going to be gravitational potential energy, because the car was at rest initially, and it was at a height of 5 meters. So we can calculate the gravitational potential energy using this equation. That's the initial energy. And then down here, we can calculate final energy. And here, we are assuming that this level is y equals 0. So there is no gravitational potential energy. There is only kinetic energy with some speed v final. So the final energy is only kinetic energy. So we have the initial and the final energies. We can set them equal to each other according to conservation of energy. So we have initial energy on the left side, final on the right side. And then you can rearrange the equation, solve for the speed. You get 9.9 meters per second. So in this case, initially there was only gravitational potential energy, and it got converted to kinetic energy. Okay, so that's the energy transformation taking place. Now, here we have chosen y equals 0 at the bottom, and we chose y equals 5 at the top. We could have flipped it as well. We could have chosen y equals 0 at the top and y equals -5 at the bottom. In that case, we would have 0 energy to start with initially, and then the final energy would be part kinetic and part gravitational. But in that case, the energy transformation still remains the same. Energy goes from gravitational to kinetic. Okay, so how do I know this? I know this because if the gravitational energy up here is 0, and then it goes down, the energy down here will become negative. Okay, so the gravitational energy goes from 0 to negative. It's decreasing, and as it's decreasing, the kinetic energy is increasing. So gravitational energy is being converted to kinetic energy, and in the process, gravitational energy decreases and kinetic energy increases. Okay, so no matter how you choose the coordinate axis, you will always have the same type of energy transformation. So when you change the axis, what changes is the reference point. You're going to change where you consider the gravitational energy to be 0. Okay, now we have one more type of energy to study, spring energy. Okay, so symbol we use is U subscript SP. And you can look at this simulation here. So here we are pulling a string or pushing a string. So we are extending or compressing the spring here. And the simulation shows you the potential energy stored in the spring as you extend or compress it. Like in this picture, the equilibrium length of the spring is shown by this green dashed line. And here the spring is compressed. It's made shorter by 0.784 meters. Okay, and to do that, the spring has to apply 235 newtons the force at its compression. Okay, so at this compression, the spring has to be pushed with 235 newtons to the left, and the spring is pushing back with the same force. Okay, however, let's look at the energy involved. Okay, so when the spring is at equilibrium position, so at the dashed line, it would be at 0 potential energy. Okay, so you can see the blue line here reaches 0. So that's the plot of the energy goes to 0. And then as you compress the spring or you extend the spring, so you change the length of the spring, the potential energy increases. Okay, so in whether you compress or extend, as long as you change the length of the spring, the potential energy increases, becomes more positive. However, let's look at the shape of the graph here. The potential energy doesn't change as a straight line. It's not linear. It changes like a parabola. It's quadratic. Okay, So that's something interesting here, that as the more you compress a spring, the energy changes by a bigger fraction, by a bigger proportion. For example, suppose you compress the spring by, let's say, 0.1 meter, you'll have a certain energy somewhere over here, and then you double the compression, go from 0.1 to 0.2, the energy doesn't double, the energy becomes 4 times bigger, okay? So the energy changes as a factor of the square. And if you triple the compression, go from 0.1 to 0.3, the energy doesn't triple, energy becomes 9 times bigger, because again, you're squaring the change, okay? So this is related by this equation here. Spring energy equals half times K, which is the spring constant, okay, times x square, and x is the displacement. It's also called delta x, so you can use x or delta x. So you can see the equation has an x squared term in it, which tells us the energy changes quadratically. That means you change x by a certain factor, spring energy changes by the square of that factor. Okay, and also it doesn't matter whether x is positive or negative because you're squaring it. So the energy will always be positive. Okay, just like shown in this diagram here, you can see that the blue graph is always positive. It doesn't matter whether you extend it to the right or compress it to the left, the spring will always have positive energy when it changes the length. It will only have zero energy exactly at equilibrium. Okay, so let's look at this slide. Let's look at calculating the spring energy from the work done on the spring. Okay, so remember that when you compress a spring or extend a spring, you experience a spring force, and the spring force is not constant. So we have studied Hooke's law earlier that says that the spring force depends on the delta x, which means the more you compress or more you extend, the bigger the spring force becomes. And then you also have to factor in the spring constant K, and the negative sign tells you that the force is opposite to delta x. Okay, so the force acts opposite to the direction of the change in the spring length. Okay, so if the force isn't constant when you're extending a spring, that means the work done cannot be calculated by this equation, the F times delta x times cosine theta, because the F isn't constant. So you have to figure out a way of incorporating a force that's not constant. Okay, so how do you do that? You do that using a graph. So you plot a graph of force and distance, so force on the y-axis, delta x on the x-axis, and the area under will give you the work done by the spring. Okay, all right, so this is what we have. So we are plotting force on the y-axis, x on the x-axis, and we calculate the, we measure the spring force for each displacement here, make a graph, and the graph makes a straight line. So we have seen this already. That's what we get from Hooke's law. Now, here this graph represents the different forces at different levels of compression, extension shown on by this picture. Now, let's look at the area under this graph. Let's look at the area of the shaded triangle. This area gives us the work done when we compress the spring from 0 to all the way. Okay, so let's try to find the area under this graph. Okay, so this area under the graph will be the work done on the spring, and we know when you do work on something, you change the energy. So in this case, you're doing work on the spring and you change the spring energy. So this area effectively gives you the spring energy when you compress the spring. Okay, now how do you find the area of a triangle? It's half multiplied by the height multiplied by the base. Okay, so in this case, base is x. Okay, and the height is force. Okay, so we are not using the numeric values here. We'll just call them x and f, because it applies to any numeric value as long as you have a straight line. Okay, so this so we have spring energy equals half times x times f. Now let's look at the force. So here we're talking about the force applied on the spring. Okay, so when you're applying a force on the spring, so you're pushing on a spring, the spring pushes back with a spring force. Okay, so and the spring pushes back by the exact amount of force that you apply. So in other words, however much force you apply on the spring applies an equal amount of force. So this tells us that this force in the equation, we can replace it with Hooke's law, the spring force. And what spring force is given here? It's K times delta x. Okay, so we are ignoring the f here, the negative sign here, because the the negative sign is the direction of the spring force. But this force in the graph is the force that you apply on the spring. It's not the spring force. So basically, this is the force opposite to the spring force. You're applying it on the spring. So you don't need a negative sign because the force that you apply on the spring is already opposite to the spring force. And that's like saying that you're taking a negative of a negative force. You get a positive force here. Okay. So you end up with half times x times kx, and that gives you the equation we're looking for, half times k times x squared. That's the spring energy stored for a compression of x. So let's look at this problem. We have a 200-gram block on a frictionless surface, and it's pushed against a spring, and the spring constant is 500 newtons over meter. Okay, that's the unit for spring constant. And when we apply this force, the spring is compressed by 2 centimeters. Okay. All right. So then the spring has been compressed and the block is pushed against the spring. Then you release the block, and the block shoots away. Okay. So we are trying to calculate the speed at which the block shoots away from the spring. So this is our setup. The spring is compressed. So that's the initial state. And then you release the spring. The spring is not compressed anymore. It becomes at equilibrium. So that's the final state. Okay. So let's calculate the initial energy. So at the initial state, there is only spring energy because the block isn't moving and the spring isn't moving either. So you can calculate the spring energy using the numbers given here. You have the spring constant K, you have the delta X, spring compression 2 centimeters, convert to meters. So your initial energy is just spring energy, half times K times X initial square. Then for the final energy, the spring is not compressed anymore and the block is traveling. So there is only kinetic energy of the block and the spring doesn't have any energy. Not kinetic, not spring. Okay. So only kinetic energy is the final energy. So you use the equation for kinetic energy, half times mv square. So you have an equation for initial energy and final energy. You set them equal to each other using conservation of energy here. And now plug in the quantities. So plug in the initial energy on one side, which is the spring energy, and then the final energy on the other side. So rearrange the equation, solve for V final, and you can see the halves cancel out on both sides. So we get V final equals x initial square root of k over m. And we know what x initial is. It's the 2 centimeters, and we are given the values of k and m. Remember to convert the m from 200 grams to kilograms. So you would get 0.2 kilograms. So plug everything in and calculate, you get 1 meter per second. Okay, so that's the speed of the block after it has been released. So when it's not in contact with the spring anymore, it's traveling on its own, it will have this much speed. Okay, so here, as long as the block is in contact, like as long as the spring is returning to equilibrium, the speed of the block will increase. But once the spring reaches equilibrium, the block is released from the spring, it's not in contact anymore, and the block travels at this speed. Okay, next problem. We have this block located 4 meters above ground level. It is a mass of 10 kilogram. It rolls down this hill, then it just travels on the horizontal surface, then hits a spring. Okay, and the spring becomes compressed. It's compressed by 2 meters. Okay, so based on this information, we are trying to figure out the spring constant K of the spring, and let's assume there is no friction anywhere. So let's use conservation of energy. Initial energy equals final energy. Okay, so what's the initial energy? So initial energy is just going to be the energy of the block at the initial state, at the top of the hill. Okay, because remember the spring is not compressed at this point, so spring is at equilibrium. So there is no spring energy at the initial state. Okay, and then the block hits the spring becomes compressed. So at the final stage, when the block has come to rest, okay, so the block isn't moving now, but the spring has been compressed, so the spring has some final energy. So the final energy is spring energy. So that's what we plug in over here. So plug in gravitational energy for the initial and plug in spring energy for the final. Okay, and then plug in the equations for gravitational energy. That's mg times y, and spring energy is half times k times x final square. Okay. Rearrange the equation, solve for k. We get k equals 2 mgy over x final square. And then plug in the numbers. So the m is 10 kilograms, g is 9.8 meters per second square, y is 4 meters and x is 2 meters. Okay, so x is how much the spring is compressed, so that's 2 meters. So plugging them gives you the value of K of 196 Newton per meter. Then problem 3. So here again we have a spring with a spring constant of 300 Newton over meter, and it's compressed to a distance of 6 centimeters. Okay, so we are compressing the spring, and the spring is gaining spring energy. Then we place a ball of mass 0.2 kilograms on top of the spring and then release the spring. So the spring was compressed and there's a ball on top of it. So when the spring is released, it transfers this energy to the ball, and the ball travels upwards, goes vertically up. Okay, and then the ball keeps traveling up, so as it's going up, it's gaining gravitational potential energy, and at some point which is maximum. Okay, so we are trying to figure out this maximum height, how high above the point of release the ball travels. So again we use conservation of energy. So initially there is only spring energy because the ball is at rest and the spring has been compressed, and the final energy only is gravitational potential because it says the maximum height of the ball. So when the ball is at the maximum height, it's not moving, so there is no kinetic energy. So spring energy is the initial, gravitation is the final, so you set them equal to each other. Okay, so that's from conservation of energy. Then you plug in the expressions for spring energy and gravitational energy, and you're solving for y, so the height. So rearrange and solve for y. We get y equals k times x initial square over 2 mg. Then plug in the numbers. K is 300 newtons over meter, x is 0.06 meters, so 6 centimeters makes 0.06 meters. M is 0.2 kilograms and G is 9.8 meters per second square. The calculation gives you 0.27 meters. Okay, and this applies when the ball is launched vertically upwards, because when it's traveling vertically, we know for sure that the ball comes to rest at its peak. If it's launched at an angle, the ball is not at rest when it reaches the peak. It travels horizontally. So you can look at the discussion on projectile motion to understand this. Now, let's look at the work done by friction. Okay, so we know that when there is a force acting on an object, and the object is moving over some distance, we say the force does some work. Now, think of friction. Friction is the force. If an object is moving on a surface, then friction acts on the object and tries to prevent the object from moving. Okay, so in other words, the object slows down and loses kinetic energy because of friction. So friction is doing work on the object and removing energy. It's doing negative work. Okay. All right, now the equation for work done is this: force multiplied by delta x times cosine theta. And in this case, we are looking at the force done by friction. So we replace the force with frictional force. Okay, and then let's look at the direction here, theta. So theta is the direction, is the angle between the arrow for friction and the arrow for delta x. Now we know that friction always points opposite to motion. So suppose delta x is pointing to the right, friction will point to the left. Or if delta x points to the left, friction points to the right. So friction always points opposite to delta x, opposite to motion. So this angle theta is going to be half a circle. It's going to be 180 degrees. Okay. And when you plug in cosine of 180 degrees, you get -1. So this gives us a more compact expression. Work done by friction is negative times friction times delta x. All right, now something to keep in mind is that the forces that we have seen before, gravitational forces and spring forces, they can add energy or remove energy. Okay, so like a spring, you compress a spring, then you're adding energy to the spring, then you release the spring gives the energy back. So so it goes both ways. You can transfer energy in and out. However, friction doesn't work like that. Friction is dissipative, also called a non-conservative force, which means it always removes energy. Okay, so it will never give the energy back. Okay, so that's a big difference between these forces and friction. That friction is dissipative, while these other forces are conservative. They will conserve energy, but friction won't. Now, back to our simulation with the skater. So again, we have a skater on a track but this time there is friction on the track. Okay, so you put the skater somewhere on the track using this simulation, then let him slide down. So as he's traveling down, we'll see that his a thermal energy increases. Okay, so thermal energy is caused by friction. So there is friction between the skater and the track, and because of friction, the system heats up. Either the skater or the track or both heat up. Okay, so you will see it when you run this simulation that like before, we have a bar for kinetic energy and potential energy, and they're changing height. So some kinetic goes to potential, and then sometimes potential goes to kinetic. But at the same time, we'll have this bar for thermal energy that shows that the some of the energy is being converted to heat. So you will see this bar rising as the skater travels. And this also means that if the skater starts from the top of the track and you release him, because of friction, he won't be able to reach the other end, other top. He will have lost some energy, and he will end up somewhere close to the top, but not exactly. And then the next cycle, as he rolls down and goes back and forth, every time he's losing energy, and because of that he's slowing down because he has less energy and less kinetic energy, and eventually he will settle at the very bottom. Okay, so this is known as energy lost by friction. Friction removes kinetic energy and transfers it to heat energy. So let's look at conservation of energy once again. So earlier we said that if there is no external work done, like if there is no friction, for example, then conservation of energy gives us energy initial equals energy final. However, if there is friction, this is not true anymore. Energy initial is not equal to energy final. Instead, you have to factor in the energy lost by friction. So you write it like this. Energy final minus energy initial equals work done by friction. So basically this is saying the difference between the energies initial and final is accounted for by the work done by friction. And then for the work done by friction, you can use the equation from a couple of slides ago. Work done by friction is negative friction times delta x. So let's look at this problem. We have a 10 kilogram desk, and it's being pulled at 5 meters per second along a flat surface, and the coefficient of friction is given, 0.2. And then the rope breaks. So at the point the rope breaks, the the desk has a speed of 5 meters per second, and then there's friction acting on it, so slowing it down. So we are trying to calculate how far the desk will slide before it comes to rest. Okay, so we can do this problem using kinematics equations, using velocity, acceleration, displacement, but you can also do this using energy. So let's do it with energy here. So let's write down what we know. We know that the final energy is 0 of the desk because it comes to rest, and it's on a horizontal surface. And the initial energy is just kinetic energy. Okay, so it was moving with a certain speed. And then this is how we calculate friction, the coefficient multiplied by the normal force. So what's the normal force for this object? It's on a horizontal surface, and there is no acceleration in the vertical direction. So normal force is just mg. So you use the equation for energy and friction, work and energy from the previous slide, that U final minus U initial equals negative friction times delta x. And then plug in the quantities here. So final energy is 0, initial energy is half mv square, and work done by friction is this, negative mu mg delta x. Okay, so we are trying to solve for delta x, so that's how long friction, that's over how much distance friction acts before the object comes to rest, comes to the final state. So rearrange, solve for delta x, and you get this, negative half mv square divided by negative mu mg. So the mass of the table cancels out, and then you plug in the values for other quantities. So v is 5, then mu is 0.2, the coefficient, and g is 9.8 with the proper units. You get 6.37 meters. Okay, so here's a variation of the same problem. This time, again, we have a desk being pulled at 5 meters per second, but this time the desk is traveling up an incline. So the incline is 10 degrees from the ground. And again, the rope breaks, and we are trying to calculate how far the table travels up the hill before coming to rest. Okay, so we are still trying to find delta x, except that delta x is now pointed up this incline. So this tells us that the object, the disk, will be gaining potential energy as it travels. Okay, so on horizontal surface, it travels a certain distance before coming to rest. On a inclined surface, it will travel a smaller distance because it's losing energy faster. It's losing energy to gravitational energy as well. So let's set it up. So we have the final energy, which is just gravitational energy. Okay, so final energy is not zero for the disk because it has traveled some height. So we'll call it gravitational energy, and the equation is mgy final. And the initial energy is just kinetic energy like before. And the friction is mu times normal force. Now, on an incline, the normal force is not the same as the weight. Okay, so normal force is mg cosine theta for an object that's traveling along this incline only. Okay, so normal force is mu times n, that's mu times mg cosine theta. Okay, so this is an equation you can look up from the discussion on the object on an inclined plane. Okay, and now let's also look at the height traveled. Okay, so let's consider this triangle here. So let's take the delta x and then construct a triangle. Okay, so delta x is the hypotenuse of this triangle. So let's draw an arrow for this. And then y, okay, so y final is the height of the triangle. Okay, and this angle is the same angle as theta. So in this triangle, we have the hypotenuse delta x, and we are trying to find the vertical side y final. So we can write down y final like this. Y final equals delta x sine of theta. All right, so just use a little bit of trigonometry, do sine of theta, and from there solve for y final. You get this. Y final equals delta x sine theta. So this gives us a conversion for y final in terms of delta x, okay, because we are trying to find delta x anyway. So we have these quantities here. So write down the energy equation. U final minus U initial equals negative friction times delta x. Then plug in gravitational energy for U final, kinetic energy for U initial, and then plug in the expression for friction on the right side. Okay, and once you get to a y final, you can replace the y final with delta x sine theta. Okay, so just as we have done over here. Okay, and then for the other quantities, you're solving for delta x, so you can rearrange the equation, try to solve for delta x. So you might have, so when you do that, you get something that looks like this. So remember that you have two delta x's in the equation, the delta x from the first term and delta x from the right side. So you have to bring all the terms to the same side, then factor out delta x, and then solve for delta x. So this is what you get. Delta x equals half v final square divided by g sine theta plus mu g cosine theta. Okay, so you have to factor in the sine theta from the calculation for y, the height, and the cosine theta for the normal force. Okay, so they both show up here, and then you plug in the numbers, you get 3.44 meters. So as expected, the disk is traveling a shorter distance than in the previous case on the horizontal surface. So let's also revisit this problem, the object sliding down a hill. So we still have the 10 kilogram object sliding down a hill of 4 meters, then hits a spring, and the spring is compressed by 2 meters. But then we also add this part here. So there is this red part on the surface of length 0.5 meters, and there is friction on this red part. Okay, and the coefficient of friction is 0.25. So based on this information, we are calculating the spring constant K once again. So we use the work energy relationship, U final minus U initial equals work done by friction. All right, so U final is just the spring energy, like in the similar problem that we did earlier, and U initial is gravitational potential energy of the block. Okay, so there is no energy of the spring initially. Work done by friction is negative friction times d. Okay, and then for friction we know that friction can be written as mu times mg, coefficient multiplied by the weight. Okay, and then d is the distance of only the part of the track where there is friction. That's the red part. Okay, not the rest of it. Okay, so we got your equation is solving for k. So rearrange the equation, move the mgy to the other side, then divide by half x final square, we get this. K equals 2 times mgy minus mu mgd divided by x final square. Then plug in all your numbers, you get 189.9 newtons per meter. Okay. So we can see that this time we have bigger spring constant because as it turns out, the block hits the spring with a smaller speed. Okay, so it went through this red region with the friction, so it was traveling slower when it hit the spring. And the spring was compressed by the same amount as the previous question, as the original question. So this tells us the spring was less stiff. It has a smaller spring constant. Okay, and some quick overview of topics that we won't be covering in detail. So we have rotational kinetic energy, then conservation of angular momentum, and then elastic and inelastic collisions. So we discussed kinetic energy. There's linear kinetic energy. So there's linear kinetic energy for object moving in a straight line, and there's rotational kinetic energy for objects rolling. Okay, so let's look at this picture here. So we have a solid sphere that's rolling down this incline. So at the top, it has some initial energy, gravitational energy, and at the bottom, it has some kinetic energy. Okay. However, this object is rolling, it's rotating. So we have to use the equation for rotational kinetic energy. Okay. So this object will have rotational kinetic energy because it's rotating, but it's also traveling downwards. So it's moving linearly. It will have linear kinetic energy as well. So these are the energies that are concerned. We have the gravitational potential energy, and we have the linear, the translational kinetic energy, and then we also rotational kinetic energy. So both the kinetic energies added together will give you the energy at the bottom of the hill. Okay, and you can set that equal to the energy at the top of the hill. Then let's look at conservation of angular momentum. So we studied linear momentum for objects that are colliding, for example, or exploding. But then for objects that are rotating and then colliding or exploding, you have angular momentum. So like this example here, you can see this skater is rotating, spinning around the skates. So this skater has angular momentum. Okay. And you can also use conservation of angular momentum. So when we use conservation of linear momentum, we had objects traveling in straight lines that were colliding in one dimension or two dimension. And then for rotating objects, like a number of disks, you can have multiple disks colliding, and then you have to factor in conservation of angular momentum. Okay. So just like linear momentum, the angular momentum of a system will be conserved as long as there is no external force, external torque acting on the system. So the objects are only interacting within themselves, not with something outside the system. All right, and then we have collisions. So there is something called perfectly elastic collision, where the mechanical energy is conserved. That means the energy of the objects that are colliding before and after are the same. There has been no energy loss anywhere else. It remains kinetic all throughout. And then there's something called perfectly inelastic collision. And that's where two objects collide and they stick together after collision. Okay? And in that case, they lose maximum energy. Okay? So in that case, kinetic energy is not equal to the initial energy is not equal to final kinetic energy. Some energy has been converted to kinetic from to other forms. Usually like, let's say, heat, thermal energy. So thermal energy usually is at zero in cases. So real collisions are usually not perfectly inelastic or perfectly elastic. They are in between. So they conserve energy to an extent, not perfectly, and they don't lose maximum energy either. Okay. So these are about conservation of energy for types of collision. But something to keep in mind is that regardless of whether energy is conserved or not, momentum will be conserved, assuming that there is no external force acting on the system. So there is no external agent applying a force on the system. It's just the objects in the system colliding with each other. In that case, momentum is conserved, and energy may or may not be conserved. So that depends on the type of collision, the objects colliding, and so on.